Hey everybody, welcome back to chemistry. And so we are continuing through the kinetic molecular theory. So now I want to look at a specific couple of properties that gases have. I want to look at the speeds or velocities that molecules in a sample of gas will have. Also, I want to look at the kinetic energies that the molecules of a sample of gas will have. So what I'm first going to do is I'm just going to look at, say, a particular individual gas, which will be oxygen, and then we're going to start comparing gases and looking at how the kinetic energies and the velocities of different gases compare. Okay, so to start with, let's just look at a particular gas. Let's say we have a sample of oxygen gas, and it's at 27 degrees Celsius, which is 300 degrees Kelvin. Now, let's say you have a mole of it, and so you know a mole of gas occupies about 22.4 liters of space, and that in that mole of gas, there are a lot of molecules. There are 6.022 times 10 to the 23 oxygen molecules. And so a reasonable question to ask is, at room temperature, do all those molecules in that one mole of gas, do they have exactly the same speed? In other words, maybe at a particular temperature here, maybe they're all traveling, for example, at 692 miles per hour. Is that true? And the answer is no. When you have a sample of gas, that's not true at all. They don't travel all at the same speed or velocity. What they do is they have a mixture of speeds or velocities, which can be described by a distribution on a graph. So what I want to do is now I want to draw a graph of the speeds or velocities of oxygen molecules at a particular temperature. So I will draw this graph here, and so on the x-axis I have increasing speed in meters per second. You can call it velocity if you want, and so it goes out to say 1,000 meters per second. And then here on the y-axis I have the relative number of molecules, and so as you go up the y-axis, then that indicates that we just have more and more molecules at a particular speed. So the graph might look something like this. So here at very low speeds you have relatively few numbers of oxygen molecules, but then what happens is it peaks out at a certain speed. And then it trails off like this. And so this is a reasonable graph of the distribution of the velocities of oxygen molecules when you have a sample of oxygen. So here what we can do is we can notice at what speed do we have the largest number of molecules. And so here, this may be the most frequent speed or velocity. So we'll say V for velocity, and for the most frequent speed, we'll have an F there. Now, what you can do is you can sort of look at this distribution and see what it looks like. And you can sort of see it doesn't look exactly like a bell curve. You can see that on the right side, the higher speeds, it tends to trail off a little bit. And so this is not really a bell curve. This is a different curve with a different name. It's called a Maxwell-Boltzmann curve or a Maxwell-Boltzmann distribution. And so here, I'm just going to mark that here. This is a Maxwell-Boltzmann distribution. Now, one thing we can do is we can characterize this Maxwell distribution of the speeds of the oxygen molecules by looking at its average velocity of the molecules. So here we have the most frequent velocity, but here's the thing. The average velocity of these molecules here is not the same as the most frequent velocity. In fact, the average velocity will be about here for oxygen at 27 degrees C. It'll be about here. And so this is the average velocity. So to indicate that this is an average velocity, we'll put a V there and we'll put a bar over it like that. Now, this average velocity is calculated in a particular way. The way we describe the calculation of this average velocity is something called root mean squared, which is RMS. So I'm going to say RMS here. And so we can characterize this population of oxygen molecules at 27 degrees as having an average root mean squared speed of about 480 meters per second. And if you're curious as to how fast that is in miles per hour, it's pretty fast. It's about 1,100 miles per hour. So right now you are being struck by oxygen and nitrogen molecules that are going at about that speed. And so you might wonder, why aren't they hurting me? And the reason is because these molecules have such a tiny little mass, you're not going to feel much of anything. So these are going at about 1,100 miles per hour. Okay, so one thing I need to do is I need to talk a little bit about how we characterize the average speed of these molecules. So I just kind of pointed out that it's done by making a root mean squared calculation. So I just want to briefly mention how that's different than calculating a regular average. So the way you calculate a regular average is you calculate something called an arithmetic mean. And so what an arithmetic mean is where you just add up all the molecule numbers and divide by the total number of molecules, and that will give you an average number. And so that would be the arithmetic mean. So if you were to write an equation for this, it would be something like this. Maybe the speed of one molecule plus the speed of another molecule, and just add them all up, and then you just divide them by the number of molecules. And so when you calculate an average this way, we'll just call it V bar, and we're not going to have any kind of subscript here, but this is something called an arithmetic mean. Here, what we're doing is we're calculating the average in a little bit different way. It's called a root mean squared average. And so the formula for that is on the screen. And so here we have V bar, and then we write RMS for root mean squared average. And so you take the speed of one molecule and square it, and add it to the speed of the next molecule and square that, and so on. And then you divide this by the number of molecules and take the square root of all that. And so that will give you an average called a root mean squared average. So how does the root mean squared average compare to the arithmetic average? Well, it's either the same value or it's a little bit greater. And so this in part sort of explains why the root mean square average is kind of maybe a little bit shifted away toward the higher speeds from the most frequent speed that we have here. There are two reasons for that. One, as you can see, is that this graph is not a perfect bell curve. It tends to taper off to the high velocity side, so that drags the average out to the right. But another reason is because this is a root mean squared average calculation, and it's probably going to have a higher number than an average calculated through the arithmetic mean. Now, do you need to know these equations for your homework or your test? No, but you should know that a root mean squared average is a little bit different in terms of its calculation than an arithmetic average. In fact, I have a hidden slide in the presentation that shows how you would calculate an arithmetic average speed for molecules and then compare that to the root mean squared calculation. So now what I want to do is I want to sort of leave talking about the velocities of oxygen molecules and go out to their kinetic energies. And so what I want to do is produce a graph of the kinetic energies that oxygen molecules will have in a sample of oxygen at 27 degrees C. So what might that distribution look like? Well, that's actually pretty easy to figure out, and let me show you why. So do you remember the formula that relates kinetic energy to velocity? So if you take velocity of a molecule and you square that, and you multiply it by the mass, and you multiply that by 1/2, that is going to be equal to the kinetic energy of the molecule. So what you can pretty much see is that for any velocity that a molecule has, you can multiply by some kind of constant and get the kinetic energy. And so for all these velocities, there are proportionate amounts of kinetic energy. And so what you would expect is the shape of the kinetic energy graph to be exactly the same as the velocity graph. So now we're looking at the distribution of oxygen molecules' kinetic energy. Is going to look something like this. It looks pretty much exactly the same, and there's going to be an average kinetic energy. You can call it a root mean squared average if you want to. But that's pretty much all we're going to say about that. Okay, now the next thing I want to do is I want to compare two gases. What I want to do is compare the kinetic energy of, say, oxygen and helium, and also want to compare the velocities of oxygen and helium molecules. And so let me go ahead and clear some space out here, and then I'll talk about that. Okay, so now what I want to do is I want to compare the velocities and the kinetic energies of two gases at the same time. So let's first look at kinetic energies. So maybe one of the things you might remember from the postulates of the kinetic molecular theory is that if a gas is at a particular temperature, it will have a certain average kinetic energy. And all gases at that temperature will have exactly the same average kinetic energy. But it goes a little further than that. If you have two different gases at the same temperature, they will have the same distributions of kinetic energy on a graph. So there's a reason for that. The reason is the formula relating kinetic energy and temperature. So let me quickly give you that. So the average kinetic energy here is equal to 3/2 RT. And so what you can see is that the kinetic energy of a molecule is really only going to depend on its temperature and really not much else about the molecule. It's not going to depend on its molecular mass or anything else. Okay, so let's go ahead and plot the kinetic energies of oxygen molecules again at 27 degrees Celsius. And so it looks something like this. And so if you wanted to, you could figure out what the average kinetic energy of this population of molecules is. And so this is oxygen's curve. Now, like I was saying before, if you have a different gas, because it's at the same temperature, 27 degrees Celsius, it will have the same average kinetic energy and the same distribution of kinetic energies. So if we were to plot helium's kinetic energies, it would look something like this. It would be right on top of oxygen's curve, like this. And so really the distributions of helium's kinetic energies is really not going to be any different than oxygen's. And so they're going to have the same average too. So here we have the kinetic energy average of helium is going to be equal to the kinetic energy average of oxygen. So really no surprises there. Okay, now how about velocity? We can see that the kinetic energy distribution of helium and oxygen is the same. How about velocity? What will those curves look like? Well, there may be a little bit of a surprise here. And so here is oxygen's curve again, so let me draw that out. And so the average here, VRMS for oxygen is 480 meters per second. And so this is oxygen curve, okay? Now let's go ahead and onto this graph draw helium's curve. Well, helium's curve looks like this. It does not follow oxygen's distribution. And what you would find is that helium, its root mean squared average actually is quite a bit greater than oxygen's. It would be, say here, VRMS would be for about 1,300 meters per second. So this is helium. Okay, so a fair question to ask is, why do these two different molecules have the same kinetic energy distribution but have completely different velocity distributions? Well, to understand that, let's look at the relationship between kinetic energy of a molecule and its velocity. And so you know that formula. And so the formula is going to be kinetic energy is equal to 1/2 mv squared. Now, let's go ahead and sort of assign this, for example, to oxygen. So we're going to write kinetic energy of oxygen here is equal to the mass of the oxygen times the velocity squared of the oxygen molecules. And so we need a little bit more space here. So we're going to do the same formula for helium so that the kinetic energy of helium molecules is equal to 1/2 the mass of the helium molecules times the square of the velocity of the helium molecules. And so we can write that. Now, one of the things you might remember is that oxygen and helium have different masses. In fact, an individual helium molecule is considerably lighter. It's about 8 times lighter than an oxygen molecule. So let me rewrite these formulas again. So we have the kinetic energy of oxygen is going to be equal to 1/2. And so what we'll do is we'll put in the molar mass of diatomic oxygen here, which is 32 grams per mole, times the velocity squared of oxygen molecules. And we can do the same thing for helium. And then helium, its atomic mass is 4.0 grams per mole, times the velocity of helium molecules squared. And so now I think you can sort of see why the average velocity of helium is so much greater than that of oxygen. So imagine here that these kinetic energies for oxygen and helium have to be exactly the same, yet the oxygen mass is 8 times greater than the helium mass. So how can we have these kinetic energies be the same if this number for oxygen is 8 times greater? Well, then the speeds of oxygen will have to be quite a bit less. That when multiplied by 32 give you a kinetic energy that matches the kinetic energy of helium molecules, which will have higher speeds. When multiplied by 4 will give you that kinetic energy. And so that is the reason why, is that despite the fact that different gases have the same distribution of kinetic energies at a certain temperature, they have a different velocity distribution. Okay, so now what I need to do is go over to the computer and talk about this a little bit more carefully. So in this slide, what we can see here is that we have several gases. The way they differ from one another is they have different molecular weights, although they're all at the same temperature. And what you can see is that they have different velocity distributions. And also what I'm hoping you can see is that as the molecule gets lighter and lighter from oxygen to nitrogen, down to water, and it's getting lighter to helium, to hydrogen. So hydrogen is the lightest gas known. What you can see is that it goes faster and faster. And the way you represent that it's going faster and faster is that it has a higher average root mean squared speed. So here, oxygen has a root mean squared speed of approximately 480 meters per second. And then helium has an average root mean squared speed of about 1,300 meters per second. And then hydrogen is even a lighter gas, and you can see it's going to have an average root mean squared speed that's even faster than that. So it's going to be way out here. Now, there is an equation that describes this, and so let me kind of mention that. Here is the equation. This equation you will not have to do a calculation with on your test, but as I recall, you may have to do a calculation with it on your homework. And so if you want to learn how to do that, I have a presentation where I use this equation to calculate the root mean squared average speed of a particular gas. Anyway, I want to point out some things about the equation. So what you can see is that the average velocity or speed of a gas, the root mean squared average, is going to be equal to the square root of 3 times R, R is being the gas constant, T is the temperature in Kelvin, divided by the molar mass. So here, M here is molar mass. So let's think about the implications of this equation. So imagine that you're looking at different samples of gases of different identities. You're going from oxygen to nitrogen to water to helium to hydrogen. And so as you go down in molar mass, let's see how this equation is going to predict what the average speed of the molecules is going to do. So you can see that because the molar mass is in the denominator, when the molar mass gets less and less and less, the number of the denominator is getting less and less and less, and so we would expect the root mean squared average of the molecules to get higher and higher and higher. Okay, and so the final thing I want to kind of mention is to describe, if you're looking at a particular gas, what is the relationship between the molecular velocities of that gas and the gas's temperature. And so here, what we can just imagine here in this graph is that we're just looking at the same sample of gas, say this is oxygen, and we're looking at oxygen at 3 different temperatures. And so one temperature is 0 degrees Celsius, which is 273 Kelvin. Another temperature is going to be hotter than that, 1,000 degrees Kelvin. And the final temperature is even hotter than that, which is 2,000 degrees Kelvin. And so I think what you can sort of see is that if you're looking at the same sample of gas, as you increase its temperature, the molecules on average will be going faster and faster and faster. And so this is going to be represented with a higher root mean squared average velocity or speed for the gas, for the temperature. So here at maybe 273 degrees, the root mean squared average velocity of the gas, maybe if it's at 0 degrees Celsius, I'm making a guess here, maybe it's about 470 meters per second. But if you increase the temperature of the gas all the way out to 2,000 degrees Kelvin, then the average root mean squared velocity of the gas is going to be a lot higher than that. It looks like what? It's going to be about 1,500 meters per second. And then again, this is also for the same gas, oxygen. And so this equation here sort of explains that. And what you can see is that here, if you increase the temperature of the gas, so you would expect as this number in the numerator is increasing, then we're also going to increase the root mean squared velocity average of the gas. And so you can sort of see that here as well. Okay, thank you for listening, and we'll see you next time.